Okay, so hello. I'm Saurabhi. I'm currently doing this TAship as a part of my PMRF requirements. So I'm a PhD student here at IISc, and this is a course on statistical mechanics, as you already know. So in the last few classes, we had been discussing about. We started with thermodynamics, and then gradually we discussed the basic ideas of probability, and we also did solve different kinds of questions which try to look at how you can make use of the different laws of thermodynamics to actually relate different macroscopic variables. Okay, and we did see that there is this two kinds of description, the microscopic and the macroscopic description. So while thermodynamics deals with the macroscopic description, statistical mechanics somehow comes as a link between the microscopic description and the macroscopic description, and that's a very probabilistic uh, understanding of the processes. So there's a lot of uh, there can be different microstates corresponding to one macrostate, and we'll talk about it in details today itself. But the statistical mechanics comes in as a probabilistic description of something which links the microscopic domain description to the macroscopic ones. Okay, so let's get started. So here we'll talk about some basic concepts, and we'll try to solve certain questions. And if you have any doubt, you can let me know. Okay, so yeah. Now, as we okay, one second. So as we already know that, so if we talk about temperature or pressure or volume or all these quantities, these are all macroscopic quantities. Okay, and in a way, macroscopic quantities are an average of some microscopic parameters. They can be linked to some certain microscopic variables as well. Like if we talk about temperature, we know that temperature is nothing but the mean kinetic energy, right? So that means if in a region, if there are a number of particles, they can have different kinetic energies, and now the mean average of that will give you a macroscopic quantity, which is a variable for the entire system as a whole, and that comes in as a temperature, right? So it's more coarse grained parameter. Now similarly, you can also have pressure, which is which is associated with how the molecules collide with the surface, right? So now one can see what is the rate of change of momentum when it collides, and then make use of that, and from there get an expression of pressure. So these are certain things which we all of us to some extent have read here and there, like when we discuss kinetic theory and things like that, right? Now the microscopic theory of matter, which talks about positions and momentum and all that, and then there's this macroscopic thermodynamics, which talks about temperature, pressure, volume, entropy, and all that. Now, what's the connection between the two? So there comes the statistical mechanics, which is more of a probabilistic description. And it says that, so basically, if we ask the question, how can we derive the equations of states which is associated with the macroscopic variables? Okay, so how can we derive the equation of states starting from the microscopic description? Okay, so we'll solve certain questions to see how, you know, starting from a very probabilistic approach, making use of statistics, we can actually get to the same expressions and same equation of states that we had initially seen phenomenologically when we discussed about thermodynamics, right? Now, or if we want to obtain macroscopic parameters, how do we write certain macroscopic parameters in terms of microscopic details? Okay, some averaging, some integration, how are they related? So that's what we are trying to do. Now, multiple microstates can correspond to a single macrostate, and this idea is at the heart of statistical physics. Now, this brings us to the concept of ensemble, right? So as you can see here, so when we talk about macro state, suppose we are talking about macro state of some ideal gas, it would be defined by state functions like energy, temperature, pressure, number of particles. Okay, so these numbers that are these variables that are defining this system macroscopically, they're much smaller in number. Okay. While if you now talk about the same system and go to the microscopic description, you would have large, n number of particles involved there. So each particle will have some momentum and position and so on. So it's a greater, so the phase space, if we want to define a phase space, which in one case is defined by the macroscopic quantity, and here if we have a phase space defined by the microstates, obviously the space of microstates are much larger than the space of macrostate. Okay. And that is intricately linked to the very idea of this many to one correspondence between microstates and macrostate. Okay. So now what you can consider is, you can say that consider you have n copies of a particular macro state. Okay. And you say that now these n copies can be defined as particular points in the phase space. How do you define the phase space? So basically you have some n dimensional phase space based on the number of particles and the dimensions you're talking about. Now you would have some position and some momentum. Okay. So that would define your phase space, and there you would have individual points for individual microstates. Okay. And these microstates would be linked to some macrostate. Right. So now if you say that out of this n copies of macrostates, so now if there are dn number of representative points which actually signify your microstates, now if there are dn number of such points in some volume d tau, which you define in the phase space, then that, so dn by n at when limit n tends to infinity would give you the phase space density. So basically now you are saying that we know that there is one macrostate, but that can be linked to many different microstates. Now how these microstates are distributed in the phase space, that density, the phase space density, is defined by this relation here. Now for normalizing, you can normalize this to unity. Okay. And that gives you the normalized probability density function. Now, similar to what we have discussed in the last class as well. So now if you know the probability density function, you know how to find, expectation values, you know how to find ensemble averages. So what you have to do, you have to basically, if you have some quantity, some function O, then if you want to find the ensemble average of that, you have to basically take this integration, the volume integral of rho into O d tau, right? So that's the basic definition of expectation value, which we have also seen when we were discussing probability, right? Now, there's an important theorem, and this is a very important theorem when we talk about how things evolve with time. Okay. So this is called the Liouville's theorem, which says that now this phase space density, okay. One second. Someone in it. Okay, so now there is a very important theorem which is called the Liouville's theorem, which talks about how the phase space density evolve with time. Okay, and it says that the phase space density behaves like an incompressible fluid. Now this will have a lot of implication as we proceed. You'll be able to see. So it basically tells us that suppose we are in the phase space and we say that okay, so we are talking about the how the distribution is at some point PQ, okay, and we take a small volume here around it, okay, and there are certain number of microstates here. Now this evolves with time. Okay, how will it evolve? That will be determined by the Hamiltonian of your system. Okay, so how now once the thing starts to evolve, so basically if you have different particles, they would have an initial at the start of your measurement, you would have some position and momentum. Gradually they would change and they would evolve with time, right? Based on what are the equations of states, what is the like equations of motion and all that. So basically by making use of the Hamiltonian. So now these microstates or the distribution here will evolve with time, and consider that at some other time it has gone to some other point P prime Q prime, and this is the region that you have considered around it. Okay, so this is the volume for the same number of like whatever number of particles or representative points you had here, now they have evolved and they have taken up this volume. What Liouville's theorem tells us is that these two volumes are equal. Okay, so it tells us that all the pure states dn, so by pure states I'm meaning the microstates here, so all the pure states dn originally in the vicinity of pq are transported to the neighborhood of p prime q prime, but occupy exactly the same volume. So that means dn by d tau, where d tau is this volume element, that is left unchanged. Okay, so that's why rho, which is this probability density function, that behaves like an incompressible fluid. Okay, now why is it useful? So first of all, it is giving us an idea about how things evolve over time. Okay, so when we talk about equilibrium, okay, which is the thermodynamics is linked with this very concept of equilibrium, right? So you're talking about at equilibrium things don't change with uh, time, right? The temporal variation. So it's a constant value. We say that at equilibrium things equilibrate. They become stable. They become constant. So there is no explicit temporal change involved there for the thermodynamic variables. So there, this idea would be very useful. This theorem will be useful, which will tell us when things are at equilibrium, what should be your, how should the distribution be? How should your phase space density evolve? So now considering that, it's a incompressible fluid because your density is not changing. Okay, so d rho dt goes to 0. Okay, now rho can be a function of time, very like explicitly it can be a function of time, or otherwise it can be function of all the position and the momentum coordinates, right? So if d rho dt goes to 0, that means this thing goes to 0. It's just the uh, definition of d rho dt, right? So now what you can do is you can make use of the Hamilton equations, and from there you would see that you get something like this, which now relates the phase space density with the Hamiltonian. Okay, so the Hamiltonian is associated with what are the different forces, what are the different equations of motions, or what is the typical energy, how is the energy defined for your system. So that information is there in your Hamiltonian, right? Now this Hamiltonian is associated, and there is a relation now between the phase space density and the Hamiltonian, right? So this is what you get. So it tells us that if the members of the ensemble correspond to a equilibrium macroscopic state, the ensemble averages must be independent of time. Okay. What that tells us? That tells us that explicitly d rho equilibrium dt should go to 0. So this term should go to 0, which again tells you, okay, I'll just shift to. So this term should go to 0, which again tells you that now this Poisson bracket should also go to 0. Okay. What this implies basically is that the phase space density, therefore, is expected to be a function of your Hamiltonian. Okay. So that means whatever your Hamiltonian is defining your energy or defining the system, now the Hamiltonian, the phase space density should be a function of the Hamiltonian. Now it can be different kinds of functions. What we will see is the different ensembles as we talk about. Okay, so today we'll be talking about microcanonical, and there are many other ensembles. So canonical, grand canonical. So for all these different ensembles, you can make use of the Hamiltonian equations. Okay, so you can make use of the Hamiltonian equations and find the Hamiltonian density. Okay, and that is because this always holds. So that's why it tells us that for this to always hold, your rho equivalent should be a function of h. Okay. This solution implies that the value of rho is constant on surfaces of constant energy. So if you define a system with a constant energy, okay, which is the case when we talk about microcanonical ensemble, we say that you define your system, it's an isolated system at a particular energy. That's what we are talking about, right? So in those cases, that is already telling you that if your Hamiltonian, or if your energy h, if that is constant, so on the surface where your h is constant, rho should be constant. Okay, and this is indeed the basic assumption of statistical mechanics. Okay, the equilibrium idea, like, comes up that, whenever your H is constant, so rho should be a constant value for all those cases. Okay. Okay. Now let us talk about microcanonical ensemble. Okay. Now the starting point of thermodynamics is a mechanically, so you can just start with a mechanically and adiabatically isolated system. What do I mean by mechanically and adiabatically isolated? So adiabatically isolated means there is no heat input. Okay. Mechanically isolated means there is no work done. So it's an isolated system where there is no work done, where there is no heat exchange, right? So for this system, okay, the internal energy and the generalized coordinates. So suppose if you're talking about some, hydrostatic system, you can consider the generalized coordinate as volume, right? So for this system, the internal energy and the generalized coordinates, they are fixed, okay? And that is specific to a particular macro state. Okay. Now, what this is telling you is you have a system at a particular energy. There is no heat exchange. There is no work done. So it's fixed at a particular temperature, a particular energy, not temperature, energy, and it's a isolated system. So there, any state that corresponds to any micro state that corresponds to that particular energy will have a probability density which is equal. So all of those possibilities are equal. Okay. The corresponding set of mixed microstates. So this set of microstates is called the microcanonical ensemble. Okay. Now, because each of these different microstates, which correspond to that one particular macro state, and they're all equally probable, that tells us that if you have, if suppose omega is the number of states that you have, okay, number of microstates corresponding to that particular macro state, then this omega is the total microstate. So 1 by omega is your probability density function. Okay. And that is there only when your system, or only when you're considering the microstates corresponding to the fact where energy lies between E to E plus delta E. Okay. In all other cases, it's zero because your system has a fixed energy. Okay. So this is now a definition of the probability density function for a microcanonical ensemble. Okay. So now you can understand it's a constant in some range and zero otherwise. So you can always consider it as a function of h anyways. So it will always, that means the Poisson bracket will always go to zero in this case. Okay. So now once you have this, from here you can actually define the entropy of your system. Okay. So entropy is defined as k ln omega. So omega is the number of microstates. K ln omega gives you the entropy. Now, once you know entropy, you can find all different, thermodynamic variables from there. Okay, temperature, pressure, chemical potential, number of particles, all those you can evaluate. Okay. Now, what do you mean by K ln omega? Basically, what you are doing is you are trying to find the expectation value of K ln omega, right? So explicitly, if you want to write it in a integral form, this is how it will look like. So it's a volume integral of rho, which is your this term here, the probability density function, and then you are finding the expectation value of k ln omega. Omega, again, you can see rho is 1 by omega, right? So there comes the minus sign. So minus k ln rho. Okay, so you're finding the expectation value of minus k ln rho. And important to notice, you again normalize it with this term. Okay. What is h to the power 3n? We'll just come to that. Okay. But this is your integral description of entropy for a microcanonical ensemble. Now, once you have that, you already know from thermodynamics how these different, partial derivatives are related to the different macroscopic thermodynamic variables, right? So by using these relations, you can find all the different whatever thermodynamic variables that you want to find. Okay. So now, based on this idea, let us consider a system with n molecules of ideal gas in volume V and energy E. So in this case, I would always urge you that it's better you just also try to solve it while we discuss, because then it will be easier for you to get hold of the entire, like, It's a good practice. Okay. So, and if there is any doubt, please you can unmute and ask me. Okay. Now, let us consider a system with n molecules of ideal gas in volume V and energy E. Derive the expression for entropy from the microscopic description. Right? So, how do we do that? So, we know that the Hamiltonian for an ideal gas is given by this relation here. So, if we are talking about a n molecules of ideal gas in 3 dimension, you would have mu going from 1 to 3n. Okay. And p square by tm for a typical p square by 2m, it's a typical Hamiltonian for the for free particle, right? So p square by 2m, p nu square by 2m, nu goes from 1 to 3n. This is your Hamiltonian. Okay. Now we want to find first what is the volume in the phase space that is defined by this Hamiltonian. Okay. And you have to remember it's a microcanonical ensemble. So basically, we would finally go to only that part of the phase space where energy is constantly equal to E, right? For that, first we'll find a volume, okay, which encloses this region. Okay. So what we are doing is we are finding a volume D3NQ, D3NP. This is your volume element. And the integration lies for the case where H, which is the Hamiltonian, is less than equal to E, right? So you have a sphere. In this case, it will be a sphere based on whatever is your expression of H. Accordingly, your volume description will change. So you are finding the region in the phase space, which is, which is governed by the Hamiltonian. Okay. Now you can rewrite it further. Now here, because H is not a function of Q, it's only a function of P. What you can do is you can take Q out of the integral, and you know that D3 and Q is nothing but V to the power n, where V is your volume. Okay. And so the integration simplifies. So now you have D3 and P, where H, which is also a function of this individual momentums, is now less than equal to E. Now, how do you define this term? So you know that you can write E as P square by 2m, right? Summation over the summation. So that means summation over nu equal to 1 to 3n P nu square should be less than equal to square root of 2m E whole square. So that your energy is always bounded by the maximum value of E, right? So you can rewrite this here. H less than equal to E means this summation of P nu square should be less than equal to square root of 2m E whole square. Okay. So what does this mean? What is this expression about? So this expression is an expression of a sphere with radius less than equal to 2me, right? Square root of 2me. So now we want to find the volume of, so in order to solve this question, basically we have to solve this part, right? Now, in order to solve that, we will first solve something which is quite, general, and then we'll come back to this particular expression. Okay. So let us first calculate the volume of an n-dimensional sphere of radius r. Okay. Typically for 3 dimension, we know 4 by 3 pi r cube and all that, right? But now for an n-dimensional sphere of some radius r, how do we calculate the volume? Okay. So to start with, what we do is, how will the volume element look like? It will look something like this: dx1, dx2, dxn, because it's n-dimensional, and xi square should be less than equal to r square, because we are wanting to find the volume of a sphere of radius r. You can do a substitution where you write yi as xi by r, and this is how it would look like. So now r to the power n has come out of the integral, and what you have is the volume of a n-dimensional sphere of unit radius, because now the radius has become 1 because of the substitution, right? So this term, you can write it as Cn. Okay, so Cn is the volume of n-dimensional sphere of unit radius. How do we find that? How do we find this value? So we know, we make use of a very standard integral. So we know that from minus infinity to infinity, dx e to the power minus x square is given as root over pi. Okay. So now what you can do is, you can actually write, you can take n such combinations, right? And then you can write minus n to infinity for all the different values of dxi. We have e to the power minus. So individually, you have just added all these terms, right? So what would that like? You have done a product of n such expressions, and that would give you something like this, right? Now, what is this? So we know we have to find this, right? Where you have termed this value as like RNCN, where this is for the unit radius. So if you have n-dimensional volume element, which is given as dx1, dx2, dxn, you can always write it as considering a shell of a n minus 1 dimension and then add a little depth or little height to it. Like similar to the case where if you define a volume element in 3 dimension, we write it as 4 pi r squared dr, right? You consider a shell and then you consider a small thickness to it, that is dr, right? So same thing here. So if you have n dimensional volume given as dvn, you can write it as, so you can just do a derivative of this, which will give you, you know what is vn, right? Vn is given as rncn. So the derivative of that into dr, that's your a small shell volume, okay? Like similar to what we just discussed. So now, using expression for dxi, dx2, dxn in this integral, what do we get? This was your initial expression, right? So what you do, you know that ncn 0 to infinity, basically now you have added all these expressions, okay? So you would get it as r to the power n minus 1 dr e to the power minus r square is given as pi n by 2, okay? So using this, we can very easily calculate Cn. Our main aim is to calculate Cn because we need Cn to get the volume here, right? So what you do is you solve for this expression and you already know the value of the integral, right? So by definition, here you have a gamma function, and that leads to this expression for the volume of an n-dimensional unit sphere. Okay, this is the expression for n dimension. So based on the question of whatever dimension is there, accordingly this exponent, this coefficient would vary, right? So now that means Vn, which is the volume of n-dimensional sphere of radius r, is given by this expression here. Now, once you have the volume, why it is important is, so now you know how to calculate this part. Okay, this is nothing but uh, just a sphere with where the radius is given as is less than equal to square root of 2me, right? So we now know how to find this part of our expression. That will give you the volume element. So that means if we put in the value of r and the dimensions, which if we put in that value, this is how it will look like. So this is omega, which is actually talking about the volume integral, right? Now we want to find how many such, so if this is the volume element, we want to find how many microstates are there on a shell which corresponds to the fixed energy of E, right? So what you do a derivative of omega with respect to E energy, okay? And then you consider that if the, the amount of phase space covered by one microstate is given as sigma naught, then what will be the number of microstates? So if you take this entire region of the phase space and then divide by what is the region for one particular microstate, that will give you the number, right? So that is what is being done here. So now once you know omega, you can actually find entropy, which is the same formula as we had done, right? K ln omega. And you can use a very well-known approximation called the Stirling approximation in the cases where n is significantly large. So what you get, if you substitute this value here, you would get an expression something like this. Okay. So now once you know the entropy, you can find all the different thermodynamic, variables from here, right? So you can use this relation. So suppose now if you use the relation 1 by T equal to del S del E, this is something which we have derived early back in the first class. So now once you know the entropy, you can do a derivative and try to find the expression for temperature. You can try to find the expression for pressure. Okay, you can also relate the two and you can see this. So PV equal to NKT, right? These expressions we had come across this when we had phenomenologically looked at things during thermodynamics. Now, starting from a very fundamental microscopic description, we have reached the same value, same expression. Okay, so that's how these are all linked. Now, here important to note is this sigma naught, which is the amount of phase space, okay, which is covered by a single microstate. Okay, so in quantum mechanics, we know this relation called the uncertainty principle or uncertainty relation, which says that each microstate, or whenever we are actually measuring the position and momentum of some particle, we know that there is some uncertainty that is always there, and that's given by this relation, which tells us del P del Q should always be greater than equal to 1 h. Okay, so that means in 3 dimensions you can write it as del 3 n P del 3 n Q should be greater than equal to h n. Okay, what is this telling you? This is telling you that in quantum mechanical phase space, each microstate, the smallest value of the phase space that it can occupy is h to the power 3n. Okay, so that is what has been considered as the part of the phase space taken up by one microstate. Okay, now you can find, once you know S, you can find the different thermodynamic variables. There's one important point to note here. So if you look closely at the expression of the entropy, you'll find that while other things, all the derivation and everything makes sense, there's something odd with the expression of entropy. So if you look at it closely, can you tell me what is the problem with the expression of entropy? Is there any problem? There is something, but what is the problem? If you have any idea, please feel free to answer. Okay. So till now, whatever we have done makes sense. So we have looked at the phase space. We know the Hamiltonian. We have looked at the phase space. We have defined a volume which is governed, or you know as per the Hamiltonian that we have, and then we have done calculated the volume of that n-dimensional phase space. Okay. From there, we have done a derivative to actually look at the region where the energy remains constant, so that hypersurface that we are talking about, and then we divide it by what is the phase space region covered by one microstate, and that gives us the number of state. Once we have the number of states, we can find the entropy and all the other different thermodynamic variables. Till now it's fine, but there's something odd with the expression of entropy that we have here. Okay, any idea what this can be? So remember, we at the start of thermodynamics, we did discuss about things becoming either intensive or extensive properties, right? So intensive means there are certain variables which are independent of the size of your system or the number of particles, right? But then there are certain systems which do change with the size and everything. So then it becomes extensive, right? Now, is entropy an intrinsic quantity or an extensive intensive quantity or an extensive quantity? So if you have a smaller system and if you have a larger system, we always expect the entropy to vary accordingly, right? So entropy of a larger object or entropy where n is large, number of particle is large, is expected to be more, right? So it's an extensive quantity. What it means is that if you double the volume, similar change should come up in the entropy as well, right? But now if you look at this expression, does that hold? You see, you have a volume term, okay, inside a logarithm here. So that means this expression by itself is something wrong. Okay, it's not addressing, it's not giving us a extensive expression for an extensive quantity, right? It's not properly extensive. So the expression of S is not entirely correct. And where the problem lies is that here, when we calculated the number of microstates, okay, we considered that the different molecules are all distinguishable, right? So you have 100 particles, you consider each of the particle as different, and that's how we have calculated this expression of number of microstates. But that's not necessarily true, and that's actually not true, because when we're talking about ideal gas in a region, the molecules are indistinguishable, right? What that means is, because it's indistinguishable, just alternating the position or swapping the positions of different particles won't make any difference, right? They would still correspond to the same microstate. So that means the number of microstates is expected to decrease by certain factor if we consider that these particles or molecules are indistinguishable, right? And how much will it decrease? So if you can consider what are the different ways in which permutations can happen when you have some n such particles, from there you can now say that the number of number of microstate definition should now be modified within 1 by n prime factorial, 1 by n factorial term. Okay, so now considering this as your expression of the number of microstates, you can now again redo the calculation for entropy and the other thermodynamic variables. Okay. So this is important. So based on whether your system is indistinguishable or distinguishable, you have to bring in this factor 1 by n factorial. Okay. So this is called the Gibbs paradox. Okay, it's a very well-known paradox called the Gibbs paradox, which takes care of this indistinguishable and distinguishable behavior. Now, with the Gibbs correction, what we can do, so now we rewrite the expression, okay, and we again use the Stirling's formula, considering that n is sufficiently large, and from there, this is the expression that we get. So this is our expression of entropy. Okay. Now what has changed here is, you can see you have V by N, you also have E by N. So inside the logarithm term, these will, both of them, so V, E and N, all of them will increase or change proportionately, right? So they will get all. So whenever there is a change in volume, suppose that will be associated with change in N, change in E. So this term, initially you just had V here, which would always remain, right? So here what would happen is, you would have extensive behavior, which also comes in, like, because you have this term here, and this looks as the correct expression for entropy. Okay. Now, once you know this, you can find all the different thermodynamic variables that we had initially discussed. So for indistinguishable particles, Gibbs factor needs to be considered. For distinguishable ones, it's not necessary. Okay. Now, when will you tell particles as distinguishable, when not? So we like, just remember this idea that when we are talking about distinguishable particles, their position might matter, their orientation might matter. So there are other ways of differentiating the particles. Okay, they can be of different colors, things like that. While in indistinguishable particles, they are the same. Okay, so permutation of positions or all that does not matter for indistinguishable particles. Okay, so here the number of sorry, so here the number of uh, microstates that you have would decrease in the case of indistinguishable particles. Okay. So now what you can do is, till now, whatever we have discussed, we know that if you know the number of particles, number of microstates omega, from there you can find the entropy. Once you have the entropy expression, what you can do, you want to find the number of microstates, I mean, you want to find omega, and for that, you can define omega as some density of states into the energy that we are talking about. Okay. And the density of states is nothing but a derivative of this term. Okay. Uh, Derivative of this volume integral. It's same as what we had just discussed previously. So you now calculate the volume integral first, which is also governed by what Hamiltonian and what energy you are limited to, and this is your expression of the volume integral, and then a derivative of that will give you the density of states. The density of states multiplied by energy will give you the net number of particles. Okay, so this is the general protocol of solving this kind of questions, where we start with some particle distribution something, and we want to find thermodynamic or you know macroscopic variables. Okay, this is the general process. Now, based on what we have discussed so far, let's try to solve some questions. So it says that calculate the thermodynamic properties of a system of n classical distinguishable harmonic oscillators with frequency omega and microcanonical ensemble. So what do we know? We are talking about n classical distinguishable harmonic oscillator. Okay. So for one harmonic oscillator, we know this is how the Hamiltonian looks like. Now you have n such harmonic oscillators. Okay. So this is how it would look like. Okay. Now, because you have n such particles, you can define a volume integral given as dnq dnp. Okay. Do a volume integral for the energy that's inside, like, for the phase space region that's covered by this energy value. And you have 1 by h to the power n. So this is again coming from the fact that this is the smallest region of the phase space that can be covered by a single microstate. Okay. So this would give you the, what do I say, the number of uh, microstates for present in this volume. Okay. So to solve this, what do? We first look at the expression of the Hamiltonian and try to simplify it to to so that it looks like an expression of a sphere or something more general. Okay. For this case, it would be, we're trying to write it in the form of a equation for sphere with some particular radius. Okay. So you consider m omega q as x and then rewrite it. So this is how it would look like. Okay. Now, what is this part? The entire integral with this condition is telling you that this integral corresponds exactly to the volume of a 2n dimensional sphere of radius root over 2me. So in all these kind of questions, and as we proceed further also with in the coming class about other ensembles, you would see that the fact that you can find the volume of an n-dimensional sphere of certain radius, that equation, that formula that we derived, that's very, very useful in all these cases. Okay. So now you have to find the volume of a 2n dimensional sphere of radius given as root over 2me. Okay. So you can always find that, right? Just put in this expression in the formula that you have initially derived. Okay, with this is the formula. So now n becomes 2n because we're talking about 2n dimensional sphere, and r becomes root over 2me. So if you do that, you would get an expression like this. Okay, you can maybe simplify it further. So this is what comes up. Okay, we want to find the thermodynamic properties of the system. So that means we want to find entropy, temperature, pressure, or the equation of state, things like that, right? So now you know this, you have to find the density of states. So for that, what do? You do a derivative with respect to energy. So once you have the total number of microstates in a particular volume, now you do a differentiation with respect to energy to find the number of microstates corresponding to a small shell for that particular energy. Okay. So this is how it would look like. Now, once you have that, what you can do, you want to calculate thermodynamic properties, right? So you want to find the entropy, suppose. So for that, you need omega. So omega is nothing but G into E. G is the density of states, E is the energy that we are talking about. So you can now use the Stirling approximation to the formula, and this is how it would look like. Now, once you have this, what you can do is you can do derivatives and all possible combinations to find, energy, volume, number of particles, and temperature, pressure, things like that. Now, the thermodynamic properties of the system of n oscillators depend on a typical parameter. So this is important to note that also in other questions also you'll see a similar term. So this ratio is important. Okay, so this comes up multiple times in similar questions. It's the ratio of energy per particle and the typical oscillator energy. Okay, now once you have the expression of S, okay, you can try to find the equation of state. Okay, what is equation of state? So you want a relation between pressure, volume, temperature, and so on. Okay, how do you do that? So once you have S, you have to use the expression of S to find P, T, V, and all that, and then relate them. Right? That's the question. So I'll just give you a couple of minutes so that if you want to try, you can try, because these are very standard questions and very standard solutions which should come very handy. So you can just try to give it a, you know, maybe try it once. Okay. Once you know S, how will the equation of state look like? See, this is the thing that we were trying to solve. We are trying to go from microscopic description to macroscopic description. Okay. Something which I've already seen in thermodynamics. We should get the similar kinds of expressions here. You can also write in the chat box if there are questions. So see, here, once you know S, you can use this relation to find an expression for T. Okay. And this is how it would look like. So now you know a relation between E and T. Okay. Now, similarly, you can try to find an expression for pressure and heat capacities. Right. This by itself is also a equation. But now, if you have to find an expression for pressure, how do you do it? So you again know the relation between S, V, and P and T, right? These things we already know these expressions from thermodynamics. So what you can do is you can directly use this relation. Okay, this will tell you that the pressure is zero. That makes sense. Why? So if I ask you, see, whenever you're solving this kind of questions, whatever results you get, try to relate it with the physical meaning of what it is implying, right? So you are talking about an n classical distinguishable harmonic oscillators, a system of such oscillators, and the pressure turns out to be zero, right? So it should, you know, bother you that why is the pressure zero, right? What does it mean? So it is because, see, you have this distinguishable harmonic oscillators, which means it's more like they are localized at certain regions, and then they are having some kinetic energy, like some potential energy, okay, that comes in the Hamiltonian, and then you solve for the overall thermodynamic properties. But these harmonic oscillators are not free to go and collide with the surface or the boundary around it so that there's a pressure, right? They're not free. So that's the reason why the pressure turns out to be zero. So there is no surprise that the pressure should be zero here. Okay. So that's what is being written here. And now you can also try to find the heat capacity, which is nothing but del E del T, which is given from the expression here. Okay, so that's how you can use the expressions of entropy to find different other thermodynamic variables. Okay, so at constant volume or constant pressure, they have the same value of heat capacity. Because why? Because the system cannot perform any work. Okay, because this is just a system of distinguishable harmonic oscillators with oscillators being fixed at certain regions. Okay, so that's why they don't do any volume work. Okay, so we till now we talked about n harmonic oscillators in one dimension, right? So now if we try to solve it for n harmonic oscillators in three dimension, okay, what do you think will change? How will the expressions change? I would urge you to try to solve it, just have a pen paper and try to just work it out a bit, okay? This practice is useful. How will the expressions change? You now have n harmonic oscillators in three dimensions. Okay, initially it was n oscillators in one dimension. So you can understand that if we start at the very early stage of how we were starting with the question, these these things will change, right? That's where the change will come in. Change will come in all the places where you have this capital N thing, right? So basically now your I will run from 1 to 3n. Okay. Other things would be quite similar. So what happens here is when we try to write an expression for the volume enclosing the like volume corresponding to this energy less than equal to E, there you would now have a 6n dimensional volume, right? And this is how you can use the same formula that we have derived. Okay, so now it's a 6n dimensional volume of certain radius given as root over 2me. So that's the only change. Okay, so now once you do that, you again can find, you know, the number of particles or number of microstates within the energy shell from E to E plus delta E. Okay, use the Stirling approximation on the expression of entropy, and this is how it would look like. Okay, so once you now have S, you can find an expression for temperature maybe. This is how it would look like, and that makes sense, right? If you have n harmonic oscillators in three dimension, for each of the oscillators in each dimension, you have kinetic energy and potential energy. And from equipartition theorem, we know that for each degrees of freedom, you have a half kBT energy. So that means for one dimension, when you have kinetic energy and potential energy, so that's half kT plus half kT, 1 kT, right? And then you have three such dimensions that you're talking about. So that gives you the average energy per oscillator as 3 kT. Okay, and that also comes in from here. Okay, so now based on what we have discussed so far, let's try to solve some questions. And these are simple questions, but based on whatever the ideas that we have, you know, discussed so far. So consider a system of n non-interacting particles, each fixed in position and carrying a magnetic moment mu, okay, which is immersed in a magnetic field H. Each particle may then exist in one of the two energy states, either equal to 0 or equal to 2 mu h. Okay. Treat the particles as distinguishable. So first, why are we talking about distinguishable particles? So look at it. The question says that you have non-interacting particle, each fixed in position. So typically when there are things fixed in position, you can actually distinguish the particles based on their position, right? So that's why it becomes a distinguishable system. Now, because it's distinguishable, we would not have the Gibbs paradox term, right? You would not have that 1 by n factorial term. So remember that. Okay, these hints that you have particles fixed in position and all these things will tell you how to and where to use the Gibbs paradox and where not to. Okay. So now it says that so you have a system of distinguishable particles, n such particles, and each particle can exist in two states, E equal to 0 and E equal to 2 mu h. So that means the maximum energy that you can have if there are n particles is n into E, right? Minimum would be 0. Now you have to, what do you have to do? You have to first find an expression for entropy in terms of number of particles n in the upper state, right? So consider that you have n particles in the upper state given as 2 mu h. Okay. So you have n such particles. Now you want to find an expression for entropy. Always remember, on a very fundamental level, entropy is associated with randomness, right? So it's associated with how many microstates are there. It is associated with how the particles can be distributed, right? So that idea should always be clear to you. Okay. So now it says that you have n out of capital N, you have smaller number of particles in upper state. What is the expression of entropy? Okay. Can you tell me what the expression should be? It's not very difficult. Okay. Just total number of particles is capital N, and there are smaller number of particles in upper energy state. Okay, find the entropy. Remember the initial definition of entropy and how it is associated with the number of particles, number of microstates. If you're stuck anywhere, if there's any doubt, please feel free to ask. Okay, I'm just giving you time because I want you to also, do it as we proceed so that you don't have to spend much time later. It just gets practiced during the course itself. Are you trying, or is there anything that you are stuck with? Oh, okay. So, just feel free to tell me that do you have, like, how much do you know? Okay, like how much I mean, do you have a basic idea of whatever I have been discussing? I mean, the basic about, probability and how we got to this very idea of ensemble. Did you follow that? If there's any question, just let me know, okay? I mean, it can be the first class, but you can ask me the questions. Like I can try to maybe relate it with no previous concepts so that you understand. See, for this particular question, let me be very what do I say? Uh, yeah, second. So for this particular question, you can just okay, you're writing something. Yeah, yeah, sure, sure. So I'm just telling you that so far, whatever we have discussed. Okay. So we have, for today's class, what we have discussed is that you can have systems and you can define them in two different ways, broadly speaking. You can have definitions macroscopically, where you have pressure, temperature, and all that. That's a average kind of approach, right? You do some average, some mean something, and then you define some values for your system. That's a macroscopic description. And then you have a microscopic description where you look at, the Hamiltonian of your system, where you look at individual particles, their position, their momentum, what is the equation of motion of your particles, and things like that. Okay. So these are the two different descriptions. We are trying to relate the two. Okay. Now, for that, what we saw is that there can be many microscopic descriptions that correspond to a single macroscopic description. What I mean by that is, so if you consider, you know, 5 glasses of water, and they are very identical glasses, and they all have constant temperature. So for all of the cases, the macro state is the same. But individually, in all of those glasses, the number of particles moving and their position and their momentum, they will be very different, right? So all those microstates will correspond to that same macro state where the temperature is suppose 10 degree, or maybe 37 degree, right? So that means there can be a large number of microstates corresponding to one macrostate. Now, how are these microstates distributed? Okay, what is the probability density of these microstates? Based on that, we have different kinds of, so based on how they are distributed, we get different kinds of ensembles. What is ensemble? Ensemble is basically collection of these microstates, right? How are you grouping the microstates for particular macro state, right? How is this grouping? How is the probability density? That is the type of ensemble. That's the definition of ensemble, right? That's how we define ensemble. Now, for microcanonical ensemble, the one we are discussing here, the energy is constant. Okay, so you're just looking at states of constant energy. And so suppose you know that the energy is E0. Now you can have 10 microstates corresponding to this energy E0. And you say that all these 10 states are equally probable. So then how do you define the probability density? You say that for each particle, each state has a probability of 1 by 10, right? So when I was talking about omega, that omega is nothing but that 10 in the example. Okay. So that means you need to find the number of microstates corresponding to that particular energy. Okay. Once you know the number of particles, 1 by that will give you the probability density. Okay. And then once you know the probability density, and if you once you know the number of microstates, this k ln omega, where omega is the number of microstates, gives you entropy. Now, once you find entropy, all other thermodynamic variables you can calculate by using the different relations that relate the different partial derivatives. Okay, so that's the gist of what we have been uh, discussing, right? Now, coming to the question that we are addressing now. It is saying that consider a system of n non-interacting particles. Okay, so total number of particle n. It is saying that out of capital N, small n number of particles are in the upper state. So there are two energy states that the particle can be in, and n number of particles are in the upper state. Find the expression for entropy. So the first thing that should come to your mind is you want to find what is the number of ways in which you can have small n number of particles in the upper state when the total number of particle is n, capital N, right? So that means you have 10 particles. You are asked what is the probability, what is the expression of entropy when you have two particles in the upper state? How will you say define that? So you will say that in how many ways can you have two particles out of 10 particles in the upper state? So this number of ways will give you the number of microstates. Okay. And from there you can find the entropy. So if you now recall things which we have, in our higher school studies when we discussed, we did study about how you can take two particles out of 10 particles and things like that, right? Very like these are probability questions, right? So then if you remember, we say that if the particles are distinguishable, then the number of particles would be given as NCN, right? So that is n factorial by small n factorial into n minus small n factorial, right? So this is the number of ways in which you can group small n number of particles out of capital N number of particles. Okay, so that gives you the number of ways in which you can have the particles in the upper state. Okay, now how will you define entropy? Entropy is nothing but K ln Q, or K ln Q for this case, or K ln omega, which is the K into log of this number of microstates possible. Okay, so that means we have to write K ln Q for this case, right? So S is K ln Q. So this is your definition of entropy. Okay, so till now, like you got the basic idea, right? Okay, so now that you have the expression for entropy, it says find the value of n for which Sn is maximum. Okay, again this is pure mathematics now. Okay, so you have a function which is given, and you say that when will that function be maximum. So we know that at maximum what happens? The derivative becomes 0, right? So what you can do is you can do ds dn and you can set it to 0. So that will give you the value of n for which your entropy is maximized. Okay. This is pure, just simple mathematics. Okay. So, so given this expression, can you tell me the value of small n? Just try to solve it out. I'll tell you the results, but maybe just give it a try. So ds dn, set it to 0. Something like this, right? So you can just, simplify it a little bit because you have logarithms involved there. So you can rewrite the same expression, okay, like this. And then you have dsdn going to 0, okay? So if you have dsdn going to 0, just do a derivative, okay? And this is the expression that you would be getting. From here, what should be the value of small n, right? That's the question. So for this to hold, right, your S will be maximum when you have n equal to n by 2. Okay, so that means if you want to plot the expression of entropy as a function of n, this is how it should look like. Clear? So this is the point where your entropy maximizes. Now, the third part. So treating E as continuous so that the system can have negative absolute temperature, right? So you got the expression for S as function of n. Now we know that if you have n particles, smaller number of particles at energy given as, this value 2 mu h, right? You can write an energy. So if you have one particle, if you have two particles, out of that, one is in energy 0, another is in energy 2 mu h. What is the total energy given as? Total energy is 2 mu h. So if you have n particles in energy given as 2 mu h, what is the total energy of the system? It's given as n into E, right? N into 2 mu h. So now that means you can rewrite the x-axis or replace the x-axis in terms of energy. Okay, energy and n, they are proportional to each other. Okay. Now, once you write S as a function of energy, we know from thermodynamics that del S del E is related to temperature, right? So del S del E is 1 by T, if you remember, right? So that means the slope of this curve will tell you the local temperature. Once you rewrite this as a function of, so rewrite the x-axis function of energy, it will have a similar, nature, okay? And then, so when energy becomes greater than half n into epsilon, where epsilon is nothing but 2 mu h, okay? So at that point, beyond that point, your slope becomes negative, right? That means your temperature becomes negative, okay? So because 1 by T is ds dE, we have T less than 0 when energy is greater than n epsilon by 2. Okay. So now what does it mean? Like why do we get negative temperature here, right? Normally, like what are the conditions? Why are we getting a negative temperature? So the reason that there is negative temperature is because your energy levels have an upper limit. Okay. So typically when we're talking about free gas, okay, so there in a gas system, the energy level of a single particle, they do not have an upper limit, right? So in that case, the entropy is an increasing function of energy. So it rises. So you always have a positive slope. So your temperature is always positive. But in cases where you have an upper limit for your energy levels that are available, there you can have situations like negative temperature, as you can see here. Okay. Okay. So now, similar question, okay? Consider a system composed of a very large n number of distinguishable atoms. So remember, we are talking about distinguishable. So in this question, if you had non-distinguishable, suppose here it was non-distinguishable, you would have an extra 1 by n factorial coming in. Okay? So remember that in your questions. Okay. So now here it says that uh, there are indistinguishable atoms, non-moving, mutually non-interacting, and they have two energy levels. It's similar to the last question, okay? 0 and epsilon. Let E by N be the mean energy per atom in the limit n tends to 0. You have to calculate entropy per atom as a function of E by N. Okay. So based on whatever we have discussed so far, we have till now discussed a very similar question, right? So here we discussed it in terms of n, where n is the total number and then small n is the number of particles out of that capital N which are in the upper state. Now you have to write it in terms of energy because you're talking about looking at E by N ratio. So you have to rewrite the similar expressions but in terms of energy. Okay. So can you try to do that? Just based on what we have discussed in the last question, you can just do it. So you don't need too much of a prior, knowledge for this. Just use this very idea of, grouping things together, how you write NCN, right? Permutation, combination, and all that, and replace uh, N in terms of energy. I'll give you a couple of minutes. Let's give it a try. So see here, similar to the last case, you consider N1 atoms in some state with energy epsilon. So number of ways of putting N1 atoms in energy state epsilon is given as N prime, uh, N factorial divided by N1 factorial into N minus N1 factorial, NCN1, right? Now with N1 atoms in state with energy epsilon, what is the energy? Energy would be written as N1 into epsilon, right? So now you can replace N1 by E by epsilon, right? So if you put this expression in in this equation, what do you get? So now you write n prime n factorial divided by, so replace n1 by E by epsilon. Okay. So now you're writing it in terms of only the total number of particles and E, which is the energy, right? So now you can also define an entropy of your system, okay, given as k ln omega or k ln q for this case, okay. Now you can use your, consider the case, because n is quite large, so you can now use your Stirling approximation. So this is also important, okay. So how do you go from this to this? Practice using the Stirling approximation, because otherwise you might do some mistakes while you are doing the approximation, okay. So this step is also very important. Just practice doing these things. So now you have S, which is given as k ln q, okay. So now you can use the Stirling approximation to simplify it, and this is how it would look like. Okay, so this is an expression of entropy in terms of E by N. So you can see, once you simplify it, you can write, you have this E by N coming up, okay, in all the terms, right? So that's how one can do these questions. I hope it's clear, okay? If there are doubts, you can just stop me. Okay. Now, here is another question. It says that the number of microstates of a gas of n particles in a volume V, internal energy U, is given. So, you know the expression of number of particles, okay? It says that you have to find how pressure, volume, and temperature are related to each other. So, basically, you have to find the equation of state, okay. So in order to find pressure, volume, and temperature, you have to first find, or you should first find something like entropy and relate it to all these different variables, right? So you know omega, you have to find entropy. By now you should know that entropy is given as k ln omega, right? So you know omega, you know S equal to k ln omega. Once you know entropy S, you can use that to find temperature or pressure, find those expressions, and then you have to relate, look at those expressions and see how you can write an equation out of these variables, okay. So that will give you the equation of state. Clear? Just maybe, so this thing still, like the question that we're trying to do is something which we can do with the knowledge that we have in today's class itself, okay. So you don't have to go much beyond today's class to solve this question for now, okay. So you have omega, you have to find S, okay. S is given as k ln omega. So maybe first try to find the expression of the entropy, okay. So using the Stirling approximation and all that, these things are very useful. Okay, like you need to practice, otherwise it will not come handy. So you'll always have, uh, you know, you might miss certain terms and all that. So try doing it, and then we'll also discuss the solution. So, but rather than doing it later, you can just try to do it now. Whether you can or not, let it be. Just maybe try to think and do it a little bit and see what you are missing. Okay, so then it will be useful for you to later, you will also know which one to practice and what to look at. Okay, you know omega, you have to find S. S is equal to K ln omega. Okay, if you have, you know, some confusion also, don't hesitate to ask. Okay. So see, these are the different options, okay, for this. E, right. Okay, so let's see the solution. I think correct. So basically, you know omega, okay, and then you have to do KL and omega. Okay, this is how you get it. Now, once you have S, you have to use the relation of, so ds, you can write it as du by t plus p by t into dv. Okay, this comes from thermodynamics. So from here, you can write del S del U at constant volume is 1 by T. So if you know this, so by looking at the expression of S, you can try to find del S del U, right? So that will give you U equal to 3 by 2 NKT, right? Now, this is similar to what we get in thermodynamics, right? Because even there, if you have N particles in some volume, okay, and there, when we are looking at uh, the total energy or the internal energy, it takes up a form of some multiples of kT. Okay, so this looks consistent. Now you can also find P by T, okay, del S del V at constant internal energy, and this is how it would look like, right? So P by T is again this value, right? So now what you can do is, you know, expression of U and T, you know the expression of P, T and V and N. So now you can try to relate all of them, right? And that would give you this answer. So yes, you are correct. Okay, that's the answer. Very nice. Very good. Okay. So now based on whatever we have been discussing so far, these are some questions which are quite simple, and just to recap the basic fundamentals. So it says that in a classical microcanonical ensemble for a system of n interacting particles, the fundamental volume in phase space, which is regarded as equivalent to 1 microstate, is given as how much? Okay, so any idea what the answer should be? So it comes from the uncertainty principle, right? We know that the product of uh, dq dp should always be greater than h for one particular dimension, one particle, right? So now you have n particles, consider it in 3 dimension. What should be your answer? I think it's A. Exactly. Very good. I'm really glad that you are participating. Okay. Now for the next part of the question, it's the definition of microcanonical ensemble. Okay. So it says that in a microcanonical ensemble, you have a system of fixed volume. It is in contact with a large reservoir B. Then which one of the following is true? So for this, you have to remember how we started with the definition of microcanonical ensemble, right? It was a adiabatically and mechanically isolated system, right? So what do you think the answer should be here as well? Just basic definition, right? Yes. So for microcanonical ensemble, you can neither exchange energy or particles, anything with the reservoir. So you're correct. Now, when we'll be later talking about canonical ensemble, there you would see that we can actually exchange. So there in those systems, you can exchange energy, but the temperature remains constant. Okay. So that means based on these different conditions, okay, whether you are, so later you would see that you can also relax the number of particles. So there can also be exchange of particles between the system and the reservoir. So then it becomes a different ensemble, right? So based on whatever ensemble we are talking about, the what do I say? The variables that define the system would change. Okay, for microcanonical system, it's the energy and the generalized what do I say? Uh, Coordinates. I mean, for hydrostatic system, it should be volume, right? Something like that. Okay, so that defines the system in case of a microcanonical ensemble. In canonical, you would have exchange of energy which is possible, and then you define your system in terms of temperature where the temperature remains constant. Okay, so that's the definition of different ensembles. Okay, now this is also something which we discussed in today's class itself. So it says that if rho represents the density of phase space, which of the following is the equation of the Liouville's theorem? So the basic idea of Liouville's theorem is that the phase space density is like an incompressible fluid. So so that means dn, so the number of microstates per unit phase space volume, that does not change or does not vary as the system evolves. That remains constant. Okay, so for this case, what do you think the answer should be? So yes, so this is important to remember this expression, because from here we get to the fact that at equilibrium this term goes away, and that gives you that you know that gives rise to this equation. Okay, and it is from here that we reach to the fact that for equilibrium, when we're talking about ensembles for equilibrium systems, your phase space density should be a function of the Hamiltonian. Okay, that's a very fundamental uh, concept. Okay, so that comes from this theory. Okay, now for a microcanonical ensemble, the phase space density inside a small energy interval remains constant, and outside such a region, it is, what should this be? These are like quite straightforward questions, right? So for if you remember how we are proceeding with the different questions for microcanonical ensemble, we always first find the number of microstates possible in the volume, and then we go to a shell, right? We do a derivative and we go to a shell corresponding to that particular energy interval, right? If you remember how the phase space density looks like, it says that when you have your energy between E to E plus delta E, you have the phase space density as 1 by omega. At all other places, it's 0, right? So that means here the answer should be C, right? I hope it's clear, no? Okay. Now, the last question here that we are discussing here, this one is quite important in the sense that it's a very common question, okay, and it comes up in multiple aspects, even in condensed matter, in statistical physics. In all these cases, this kind of questions come up multiple times, okay. So it says that the density of state of a single particle in three dimension modeled by the microcanonical ensemble depends on energy as what. So these are certain questions which is better to solve, you know, once or twice, and maybe, to some extent remember in the sense, don't memorize them, but you know some, there are certain results which are so handy and so useful that it just should stay in your mind, right? So it's something like that. These are quite fundamental things. But you can the more important thing is to get there, okay, so to solve and get to the answer. So for this, how should you approach, right? So you have to find the density of states for a single particle in three dimension modeled by microcanonical ensemble. So here you have to remember, basically you have omega, right, the number of microstates, you know that. So there, what is the energy dependence when we are talking about single particle in three dimension? That's the question, right? So if I go back to, what we have initially described, okay, we have already discussed this. Okay, so it is already there in the expression itself, but just try to, maybe look at it and let me know if you can, uh, if it's clear. So maybe here, if we stick around here, so here we know that we are looking at, we want to find the density of states, right? So basically, we want to look at how this omega depends on energy, right? For single particle in some three dimensions, okay? So by looking at this expression that you have here, what do you think should the answer be? E. Okay, let's see. I don't know what the option B is. Yeah, so 3 by 2 minus 1 half. Yeah, right. Okay, so now based on for different dimensions, so if it was in two dimensions or one dimension, accordingly your expressions would vary, right? But you have to remember and like you should be, you should practice and get hold of the basic thing, okay? And then you don't have to remember all of it, but how you get there, that basics should be, clear to you. Okay, so till now, any confusion about whatever we have discussed today? Right. Okay. Nice. So yeah, thank you. Okay. And even if later new questions come up, do feel free to ask me. Yeah. Okay. Sure. Tell me. I understand Hindi. I'm not very grammatically correct in Hindi, but yeah, I understand. Oh yeah, that's not a problem. Like you can maybe like even if you speak, I mean, little wrong English, it will be fine. We are doing physics, so not a problem. Like so just feel free to ask questions, okay? So that's not an issue. Hindi, I don't know how much I'll be able to explain in Hindi, but yeah, I can understand basic things. I do like speak a little, but there can be grammatical errors that you have to excuse me. Yeah, okay. Okay. So any questions, just feel free to ask, okay? So even next time, if you have any question, let me know. Uh, I'll call it a day then. Okay. Thank you. Yeah. Okay. Thank you. Yeah. Thank you. Okay.